probably nice. Do you want to do that? You ready? Hello, everybody. This is Steve Thomas with bitslice does with that.
So my talk is about lop3lut. So this what is well, for starters, this is a instruction that is new to NVIDIA GPUs. What it is a 32-bit 3-operand lookup table. So basically, there's an input, 3 inputs of 32 bits, an output of 32 bits, and an 8-bit truth table. So how it works? So the the input, that's all the possible values for the 3 variables. Then the output, you can choose to be whatever you want, and this changes the way the lookup table works. So for this example, this is bit select. So the first column, that is the bit that selects which of the next 2 operands. So if it's 0, then it's the second operand, so 0, 0, 1, 1. And if it's 1, then it's the third operand, which then it's 1, 0, 1, 0, 1. So you can pick it to whatever you want. I am really good at MS Paint. Can't you tell? So this is the same exact lookup table from before. Oh, I should mention, previous slide, sorry, that the way this would be encoded is AC. It would be bottom up, right? Pretty sure. Yeah. Anyways, for the when you give it to the instruction, the lop3lut, you give it AC for 0x AC for the constant to tell it what the truth table is. So the black lines are the first bit. So 1, 0, 1. You can think of it as the 8-bit lookup table is an array of bits. So 1, 0, 1 would be the 5th bit. So that one. Then that's copied to the output. Then the red one would be 0, 1, 0, which is just those bits. 2, so it grabs the second one, puts that, so it's now 1, 1. Then the blue lines take the third bit from each, and then copy it over, and repeat. Anyways, so I never know how to say this word. Feistel? Fistel? Feistel? It's the what? Feistel. Anyways, so the Feistel network for DES, it's just 16 rounds of it. There's the initial permutation, the final permutation, and then the Feistel function, or the whatever, and XOR. So the initial permutation, this crazy hoopla. If you do this in software, it's really slow because you have to basically do a bunch of ands to get the right bits, then shift, and then OR it to the result, and it takes a lot of work. The final permutation is actually the exact opposite. It's going up. Oh, all these are going down. It doesn't really matter, but just know that each one of these blue circles is a bit, 64 top and bottom. The key schedule, there's more permutations. PC1, that's commute choice 1. Then you have rotates, which change depending on which subkey you're going for. Again, this is just like really hard to do in software, but in hardware, you basically just connect wire and the bits where you need it. So DES was actually made so that it's really fast in hardware. This is the PC2, which gets applied each subkey round. This is the F function. So you basically take a 32-bit block, then you expand it to 48, then you XOR it with the subkey, then it goes through the S boxes, and then a permutation. So everything up until now, the expansion round or part, it basically just expands it, copies some bits. So it's again just connecting inputs to outputs with wires in hardware. But in software, you have to do a bunch of ands, shifts, and ors to get it. Permutation, crazy stuff. Then, so this is the only part that up until now that you could literally just look at one bit at a time and do it. This part basically mixes all of them together. It needs to be a non-linear function, or as far away from non-linear as possible. Otherwise, there's cryptographic text, which actually it does. It didn't actually. It wasn't far enough away from being linear, so there are some problems with it. Now, bit slicing does. So each one of the blue balls from before the bits, you treat each one of those as its own variable. So when you're doing your code, you logically rename the variables so that so the first one would just get renamed. I assumed I'd actually be able to see this. So like it would get renamed to like the 8th bit or whatever. So all of that is for free when you separate everything into bits. XOR costs a little bit less because of after the expansion round, you then have two 48-bit integers that you XOR together, and when you're dealing with 32-bit integers, you'd actually have to like split that up. So then it's 2, but this you only have to do 48 for every 32 rounds. So when you split each bit into a variable of its own, you can then, your variables are all 32 bits. So you have 32 iterations of DES going at the same time. So the only problem that this creates is the S boxes. Once you split them all out, so each variable is the different bit in the from all the data, you can't then grab those out, then put that through a lookup table, then split them back out, because doing that is extremely expensive. So one of the best ways known currently for just like standard gates, not and or XOR. So these are all the different, there's 8 S boxes, 6 bits input, 4 bits output, and this is how many gates for each S box. You can actually find all this information and the code for it there. Smart guy. I actually forgot who it was though. But then he also, or she, also did non-standard gates. Basically, this lowered the number of gates per S-box from average of 56 per S-box to 51. So the first method that I tried, just to see how low I could get it, was taking the non-standard gates that from the previous slide, all those, then combine them. So each one of those we're using like AND and XOR. So basically, I could combine when 3 variables are used, but the output of some of that isn't actually used later. I can actually just combine those into one lookup table operation. So doing that reduced it to 36 1/4 on average. So that would be the gate counts and the S boxes for each one. So for the instruction, basically there's there's 256 different possibilities. So there's 2 that we really don't care about. One that would just output zeros regardless of what the input is. So basically it's dealing with no inputs. So outputting all zeros, outputting all ones. We don't really care about those, so we can throw those out. 1 inputs, there's 6 of them for this instruction that we don't care about. Basically the identity and then not of the different variables, because since we have full control over the lookup table, we can just logically not one of the inputs without needing another instruction. So then for 2 inputs, the most there's 16 possible ones, minus the 2 that don't matter, and then minus 4 that are, the identity and then the not identity. So we now have so 2 input and 3 input. Those are actually useful for these S boxes. So we have pick any 2 of the bit variables, and we can do 10 different operations that work on both inputs. Then if we use all 3 inputs, there's 218 different functions that we can do with all 3 of those. The way that I made this simpler is, since I didn't do any of the knotting, like a single variable not, what you can actually do is you can knot the output. So basically, when you're running through this, what you can do is eliminate half the key space by, if it's like above a certain point, what you can do is store all the, basically just knot the output so that it's on the lower half, so that when you actually try to find, when we're like doing, well, the next slide. Anyway, so method 2, basically you create a 4-bit lookup tables. So basically, when we're doing this, Anyone else nervous? Woo! Yeah. So basically, we can get rid of anything that is greater than, well, 32,000 basically for the 4-bit lookup tables, because we can just knot that so that it's on the lower half. Then when we're actually trying to find the correct one, we just map it to the lower half. I don't know if I'm actually, am I explaining this correctly? Or am I losing people? Okay. Yeah. Oh.
Now have that you're trying to solve is you have a whole bunch of additional gates available to you, and now you're trying to find even more optimal set of gates given this additional gate space that you have. And so you're actually talking about saving space when you're, or saving time when you're doing the actual logic brute forcing, correct?
Yeah.
Okay. So I'm following you. Hopefully everyone else is. Sorry.
So with that, it basically cuts the search space in half, since that top bit basically is 0, and you can not for that. Same thing goes for the 5-bit lookup table, the 2 5-bit lookup tables. I just did these for like, well, I did the first one just as like a proof of concept, just so that I could then expand it to the larger problem set of making a 5-bit lookup table. So with 3 bit selects, so basically you have, should have had a picture for this. So you have like 4 lookup tables. Then you have 2 extra bits. So you would use one of the bits to do a bit select according to which one it's supposed to be. Then same thing for the other side. Then you use the other bit to then bit select both of those. And then I guess it's easier to understand when you only have 5. Basically, you assume that the bit's 0, you have a lookup table for that. Then when the bit's 1, you have a lookup table for that. And then you bit select. Anyway, so method 3 that I was going to try, but I actually never got around to finishing at the top, doing a partial 6-bit lookup table. Basically, what I would be doing is writing a bunch of data to disk that, because this wouldn't fit in RAM. The problem set's just way too big. But you would basically fill up a few terabytes, and then you would have to go back and like sort it, and then put it into like a usable data, so that then you can work back from the basically the truth table for the 6-bit lookup table, that the SBox that you're actually trying to do, and try and merge backwards. I never finished, so I have no idea what it is. And best part is I don't have any of the data from the method 2, because that's at home. So yeah, I suck. But it's actually not that hard to write, so I'll probably do that before like Friday or something. So if you follow me on Twitter or GitHub, I'll probably put it there. Probably should have done it before I left. If my computer was on, yes. Anyway, sorry. So resources, if you feel like you want to do this, the OpenWall one, that actually explains a very similar method that I also wanted to try this. actually, I think it was pretty much. Anyways, it describes like building 5-bit lookup tables and then going backwards with something. I forgot exactly. But yeah, then that's the link to the standard and non-standard gates that you currently are using. Yeah. Questions? $36.25. That's the one I know. The other 61, 36.25. Jeez. Times 8. That's how many total. That's the average. I don't know. But actually, I have that. It is right there. If you want it, I'll put that. Yes.
So I guess I was only cursorily familiar with the lop3 or lop3lut lookup tables. So are they all constant time? So all 256 possibilities all take the exact same amount of instruction cycles? And then also, like, how many cycles does it take compared to like the standard XOR? Is it 1 cycle, 2 cycles? And do you know if they implemented it in hardware? So what do you know about the actual instruction itself?
I'm pretty sure it runs the same speed as all the other, like XOR and good slide. In the programming, the CUDA programming guide, there's a it tells you how many. So with CUDA, there's how many CUDA cores it has, but for each core, it's really weird. Like some of the newer ones, they don't have as many integer operation cores. So they say, oh hey, each there's 192, but there's only 64 or 32 integer operations. Some of the earlier ones that are kind of worthless now, but those actually had 10 integer operations and 8 floating point operations that it could do. So per clock cycle. So it's actually wait, 22 minutes. Thank you.